Just as we had a sum formula for the sum of a finite arithmetic sequence, we also have a formula that gives us the sum of a finite geometric sequence. The sum of a finite geometric sequence with n terms is given by the formula s subscript n is equal to a1 times the quantity 1 minus r raised to the nth power divided by 1 minus r, where a1 is the first term in the sum, r is the common ratio between terms. Notice we have a common ratio as we are dealing with a geometric sequence. And n is the number of terms in the sum, the number of terms that we are adding together. Now, again, I will give you all of these sum formulas. You are not responsible for memorizing them. However, it is up to you to know when to use the appropriate formula and how to use it. Let's look at an example. Find the sum of the geometric sequence. We have the sum from n equals 1 to 8 of 5 times negative 3 halves raised to the n minus 1. Now, obviously here we want to use our sum for a finite geometric sequence because we have a finite number of values, and our sequence that we are dealing with here is geometric, 5 times negative 3 over 2 raised to the n minus 1. Now, you're not always going to be told explicitly that it is a geometric sequence. So how do we know if it's geometric? Well, anytime the variable that we are plugging in for, in this case n, is located in your exponent, all right, it is going to be safe to assume that the sequence is geometric. All right, in this case, we have an n minus 1 as the entire exponent. Okay, other times you'll see it as just an n or maybe an I. If the variable that you are plugging in for is in the exponent, it's going to be geometric. So, in order to use this formula, we must know the first term in the sum, a subscript 1. Well, this sum begins with n equals 1. Therefore, to find the first term in the sum, we plug in 1 for n. That gives me 5 times negative 3 over 2 raised to the 1 minus 1. 1 minus 1 is 0, and any non-zero number raised to the 0 power is going to give me 1. 5 times 1 gives us 5 for the first term of the sum. We also have to know the common ratio r. The common ratio is going to be the value that is being raised to the exponent. Whatever is being raised to the exponent, and in this case, negative 3 halves is what is being raised to the exponent. So that is our common ratio between our terms. And finally, we need to know n, the number of terms in the sum. How many terms are we adding together? Well, our sum starts by plugging in 1, and it terminates when we plug in 8. Because our sum is from 1 to 8, we're going to have a total of 8 terms that we are adding together. All right, 8 terms is our value for n. Now that we have all these values, we can substitute them into our sum formula. S sub 8, this is the sum of 8 terms, is equal to 5 times the quantity 1 minus a negative 3 halves to the 8th power divided by 1 minus a negative 3 halves. Now, before you go and try to plug all of this into your calculator at once, which can get a bit messy, notice all the parentheses that we would have to use, let's just try to simplify a few things out. I personally like to start with the denominator. 1 minus a negative 3 halves. Well, that's the same as 1 plus 3 over 2. Getting a common denominator, that would be 2 over 2 plus 3 over 2, which gives us 5 over 2. We can now simplify this complex fraction by taking 5 here, that's out in front, and dividing by 5 halves. 5 divided by 5 halves, well, that's the same thing as 5 times 2 fifths. Notice that the 5s will cancel out and leave us with a 2 in front, right? Now we have 2 times the quantity 1 minus a negative 3 over 2 raised to the 8th power, and this gives us something that is much more manageable to plug into our calculators. So we plug this value in, we hit enter. Notice you're going to get a decimal approximation. Hit the math frac button on your calculator, and it spits out a nice fraction, negative 6,305 divided by 128 is our solution. Let's look at a couple more. Find the partial sum using the proper sum formula. Verify your solution using a calculator. We have the sum from I equals 0 to 20 of 1/2 times 2 raised to the I minus 1. Well, notice the value that we are plugging in for our variable I is located in the exponent, tipping us off that this is a finite geometric series. So we need to use our sum for a finite geometric sequence formula. S subscript n is equal to a1 times the quantity 1 minus r to the n over 1 minus r. Again, to use the formula, we must know a1, and a1 is the first term in the sum. Well, let's take a look at this sigma notation. The sum actually begins in this case with I equals 0. So to get the first term in this summation, we have to plug in 0 for I. Plugging in 0 for I, that gives us 1/2 times 2 raised to the, this becomes a -1. And negative exponents give us reciprocals. 2 raised to the -1, that's actually the same thing as 1/2. We have 1/2 times 1/2, which gives us 1/4 as the first term in the sum. Our common ratio, r. R is always the value that is being raised to the exponent. What is being raised to our exponent here? 2. R is equal to 2. And finally, we must know n, the number of terms that we are adding together. Well, because this sum begins with 0 and terminates with 20, we are going to be adding a total of 21 values together. And again, if you are having some trouble figuring out what n is, the number of terms, you can always take the upper limit of the sum, which would be 20 in this case, subtract the lower limit of the sum, which is 0, and add 1. 20 minus 0 gives me 20. I add 1, that gives me 21 terms in the summation. So now we can write out our formula. S subscript 21, the sum of these 21 terms, is equal to 1/4 times the quantity 1 minus 2 to the 21st power divided by 1 minus 2. Again, I think the easiest way to begin to simplify is to start with our denominator, right? Our denominator here, 1 minus 2. Well, 1 minus 2 gives us a -1. I can now take this constant multiple in front, divide it by -1, 1/4 divided by -1. That gives me -1/4 times 1 minus 2 raised to the 21st power. And now I can plug that into our calculator. We hit enter and we get our solution, 524,287.75. That is the sum of all 21 of the terms in this summation. And we can check our work by actually plugging this summation notation directly into our calculator. Remember, to get to summation notation, you are going to hit Math and then select option 0. Math 0 will bring up the summation notation. You can plug it in just as you see here. Remember that the parentheses that it gives you has to include everything that we see in the sum. So make sure you have all of this inside of parentheses. Doing so will give us the same answer. Couple more. Find the partial sum using the proper sum formula. Verify your solution using the calculator. Here we have the sum from k equals 3 to 25 of 3 times -4/5 raised to the k. Again, we see the variable that we are plugging in for k. It's located in the exponent. That tips us off that this is a geometric sum. We want to use the formula S sub n is equal to a1 times the quantity 1 minus r to the n divided by 1 minus r. So we need to know a1, the first term in the summation. Well, this summation actually begins at 3. So to find the first term in the sum, I need to plug in 3 for k. Plugging in 3 for k, that gives us 3 times -4/5 raised to the third power. We type this into our calculator. We hit the math frac button, and we end up with -192 over 125. We also have to identify r, the common ratio. R is the value that is being raised to the exponent. In this case, what's being raised to the exponent? -4/5. And we also have to identify the number of terms that we are adding together. Remember, whenever your lower limit of the sum is not 1, we can find the number of terms by taking the upper limit, subtracting the lower limit, and adding 1. 25 minus 3 plus 1. 25 minus 3 plus 1, well, that gives me 23. We are adding 23 values together. So S subscript 23 is equal to negative 192 over 125 times the quantity 1 minus negative 4 fifths raised to the 23rd divided by 1 minus a negative 4 fifths. Let's begin to simplify, starting with our denominator here. 1 minus a negative 4 fifths. That becomes 1 plus 4 fifths, leaving me with 9 over 5. I can now take the constant multiple that's in front, negative 192 divided by 125, and divide by 9 fifths. Again, you could also do that by multiplying by 5 over 9. That gives me negative 64 over 75 times 1 minus negative 4 over 5 raised to the 23rd power. And now I have my expression written out in a much more simple manner, so I can plug this all into my calculator to get our final answer. Now, this one doesn't give us a nice fraction. Instead, we just end up with a decimal approximation, negative 0.85837. Okay, don't be afraid to give MathFrac a shot. If we don't get a nice fraction, a decimal approximation will be fine. Let's try one more, a word problem here. A deposit of $50 is made at the beginning of each month in an account that pays 8% compounded monthly. The balance in the account at the end of 5 years is given by the equation A. Find A. So we have 50 times the quantity 1 plus 0.08 over 12 raised to the 1 plus 50 times 1 plus 0.08 over 12 raised to the 2 plus plus 50 times 1 plus 0.08 over 12 raised to the 60th power. So we have this which means we are adding up more terms in between. And notice that the difference between terms is seen in the exponent. Here I have a 1. The next term has a 2 in the exponent. The next term would have a 3 in the exponent, a 4 in the exponent. And we would continue until we get this last term of our sum, which has a 60 in the exponent. So we can actually write out this sum using summation notation. We have the sum from n equals 1 to 60. Notice we're going to have 60 terms here of this entire quantity. Notice this stays constant in each term. 50 times 1 plus 0.08 over 12 raised to the ith power. So I have the sum from I equals 1 to 60 of 50 times 1 plus 0.08 over 12 raised to the I. Again, if you wanted to use the letter N, that's perfectly acceptable. You could use K's. As long as your letter here matches your letter here, you are all set. All right, and so this is the summation notation of all of the terms added together that we see here. Well, this is a finite geometric sum. All right, so we can use our sum formula. S sub n equals a1 times 1 minus r to the n divided by 1 minus r. Again, we know that this is going to be geometric because the variable that we are plugging in for, our index of summation, is located in the exponent. I is in the exponent, geometric. So we need to know a1. a1 is the first term in the sum. Well, to get the first term in the sum, we would start by plugging in 1 for I, and notice that that's actually just this value right here. 50 times 1 plus 0.08 over 12 raised to the first power. We plug that into our calculator, hit MathFrac, and we end up with 151 divided by 3. We also have to know what R is, the common ratio. As we have said before, the common ratio is whatever quantity is being raised to the exponent. Well, in this case, 1 plus 0.08 divided by 12. And we can plug that into our calculator and actually get a little bit nicer fraction to work with, 151 divided by 50. And finally, we need to know n, the number of terms in the sum. How many values are we adding together? In this case, we are adding 60 terms together. Well, now allowing us to use our formula, S sub 60 is equal to 151 divided by 3 times the quantity 1 minus 151 over 50 raised to the 60th power divided by 1 minus 151 over 50. Again, we can begin by simplifying this denominator. 1 minus 151 over 50. That gives me negative 1 over 50. I can take 151 over 3 and divide it by negative 1 over 50. That gives me negative 7,550 times 1 minus 151 over 50 raised to the 60th power. And we can plug all of this into our calculator now. To get our answer, we get approximately $3,698.34.